Hey there, this is Miss Mantle. Today we're going to be talking about the beginnings of integration. And so let's suppose that we wanted to find the area under a curve. Well, there's no standard geometric formula for finding area under the curve. And so one way that we can approach this problem is to use a shape that you know the area for, like rectangles. We use rectangles because they're the easiest. So essentially, like, this is what early mathematicians did who, were trying to understand mathematics. It's how the circumference of a circle was derived by taking polygons and increasing the number of sides and finding the area and finding the perimeter, and then formulas for the area of a circle and the perimeter, aka the circumference of a circle, were created. So the same idea is true here. We're going to start with rectangles. We will be talking about other shapes as well, but we're going to start with rectangles because they're the easiest. And eventually, we won't be estimating, but we will be finding the exact area under the curve using integration. So the first section we're going to be talking about, section 5.1, is about areas using rectangles. And the thing about rectangles is that we can actually use different rectangles. Like, we can put them in different places. And so as you notice in the first diagram here in purple, so I've got some rectangles and it says left endpoint, the left side of the rectangle. The middle one says right endpoint, this is the right side of the rectangle, and midpoint, the middle part of the rectangle. So these things are what we call the rectangular approximation methods. So for the left endpoint, sometimes we'll see this notation, we'll see L ram or L sub n, where n represents the number of rectangles. Similarly, we could also have right rectangles, and we would call that R ram. This means right rectangular approximation method, or R sub n, and midpoint. So midpoint rectangular approximation method, or M sub n. And again, n equals the number of rectangles. Okay, so what we're going to start with is we're going to start with this curve here. This curve that we have is the curve 16 minus x squared from 0 to 4. And we're going to use 4 rectangles. I forgot to include that in our notes, but we're going to use 4 rectangles, and it'll make things a little bit easier for us. Okay, so what I want to do first is I want to kind of think about what's happening with my curve. So 16 minus x squared is a quadratic that opens down, and the the y-intercept would be up here at 16. And if I'm going from 0 to 4, then on the horizontal axis from 0 to 4, and we're going to divide this into 4 rectangles. So I'm going to essentially take from 0 to 4 and divide it into 4 equal spaces. So I'm going to divide that into 4 equal spaces, and lucky for us, those are just going to be integer values. Okay, so we call this little distance here delta x. And delta x is the width of our rectangle. And so we can calculate that, b minus a all over n, and in this case 4 minus 0 all over 4 means that delta x is 1. That's where I'm getting these units of 1. Okay, so that means we're going to be calculating L sub 4, and that means we're going to have 4 rectangles. So we're going to have 1, and then 2, and then 3, and then 4. We're going to add them all together. Okay, so what I want is I'm going to just kind of draw a little fence here. And I'm going to create a rectangle such that the left endpoint of the upper part of the rectangle is going to be on the function. So that means this endpoint here on the left is where I'm going to draw my left endpoint of the rectangle, and then I'm going to draw a horizontal line here to create this rectangle. This is my rectangle. Okay, and what I want here is let me zoom in. I want the area of this rectangle. And so the area of this rectangle, well, it has a width of 1, and it has a height. Well, that height is 16. And so the area is 16. So over here, I'm going to write 1 times 16. You can just put 16 if you want, but I'm going to put the 1 there because I want to show you a pattern. Okay, so then I'm going to do the same thing for the next rectangle. I'm going to put a little fence here, and when I connect at the top, I want the left endpoint of the rectangle to be on the function. And so then I'm going to draw a horizontal line and then make this rectangle here. And so the area, if I zoom in a little bit here, well, the width is 1, and then the height of this rectangle. Well, the height of this rectangle is f of 1. And f of 1 means I'm going to plug 1 into my function, which is going to be 16 minus 1 squared, which is 15. So the height of this rectangle is 15, and so the area is 15. Over on the right here, I'm going to put 1 times 15. And so we're going to continue with using the same process. I'm going to draw a little fence. I'm going to put my left endpoint, draw my horizontal line to create my rectangle. The width of the rectangle is 1, and the height is coming from f of 2. And so if I plug in 2 into my function, that's going to be 16 minus 2 squared, so that's going to be 12. So 1 times 12 is 12. And then the last one, my left endpoint, and I'm going to make a rectangle here, and it has a width of 1 and a height of f of 3. F of 3 means 16 minus 9, which is 7. And so this is 1 times 7, or 7. Okay, so let's go back over here and fill this in. So I've got 1 times 16 for the area of the first rectangle, 1 times 15 for the area of the second, 1 times 12, and then 1 times 7 for the third and fourth rectangles. Okay, so as you can see here, if I factor out a 1, okay, now I realize that factoring out a 1 is kind of stupid, but I'm going to factor out the 1 just so you can kind of see the pattern. And what's left over here, when I factor out that 1, those are the function values at the left endpoints. Okay, so I'm going to write this. So this 1 is the width. This is delta x. That's a triangle there. And then these here are the left endpoints. Oops, let me erase that. Let me fix this. I want to say the function values at the left endpoints. Okay, so now what I'm going to do is I'm just going to add them all together. Well, 16 and 15 is 31, plus 19 is going to be 50. And this is going to be 50 units squared. I don't know what kind of, like, I'm just going to say units. So this is an approximation of the area under this curve using 4 rectangles. One of the things we might want to consider is this an over or an under estimate? Well, if you look at where the rectangles lie relative to the curve, they're outside. Like, there's some areas that are here. Let me see if I can, there's these little areas that are here that are, I'm coloring here in red, that are actually outside the curve. And so these are overestimates. So this is an overestimate, the left rectangular approximation. Now this is just for this particular curve. If you have other curves, like this is a concave down function, if it's concave up or it's doing other things, and then it might be an underestimate. Just depends on what curve you have. Okay, now sometimes you're given a curve, sometimes you're given a picture, sometimes you're given the function, sometimes you're just given a table of values. So if I fill in my table of values here, here's x and here's y. My first coordinate 0, 16, my second one 1, 15, my third one 2, 12, and my fourth one 3, 7. Now the fourth one means when x is 4, well on this function when x is 4, y is 0. Okay, so how could I have done this left rectangular endpoint approximation using the table? Well, if you look at the values that got added together here, 16, 15, 12, and 7, 16, 15, 12, and 7, those are the, quote, left endpoints of the function, and then you just need to know what delta x is. Okay, so that's a little hint, right? So when we go to right rectangular approximation, this is going to be kind of essentially the same thing. I've got whoops. Let me undo that. Let me get my black ink here. 16, and I'm going from 0 to 4, and I'm going to use equal widths, 1, 2, 3. So delta x is still 1 because I want 4 rectangles. The difference with right rectangular approximation is that the right endpoint of the rectangle is on the curve. Oh, I did not draw that very well at all. Okay, and so then the area here has a width of 1, and then the height, well, the height here is f of 1, which is 15. The second rectangle, using the right endpoint on the function, has a width of 1 and a height at f of 2, which was 12. The third one has a right endpoint when x is 3, and so I've got a width of 1 and a height at f of 3, which was 7. And then the last one, my right endpoint is on 4, and so this rectangle, quote unquote, has an area of 0. And so then for this graph then, or this approximation, if I do R4, it's 1 times 15 plus 1 times 12 plus 1 times 7 plus 1 times 0. There's 1, 2, 3, 4 rectangles that got added together. I can take the width and pull it out, 15 plus 12 plus 7 plus 0. I can add them together, and I get 34. Let's put that over here. So we have, oops, this here. I'm learning how to use this today. So this is my delta x, and then these values are the function values at the right endpoints. And if you have the table, you can see from the table the values that we added together here are the right endpoints in the table. So sometimes making a table from the outset is kind of nice because then you can just sort of shift yourself around in the table. Delta x will not always be 1, so be careful of that, not always 1. And then the last thing I want to talk about here is with the left endpoint approximation, we said that it was an overestimate. Well, this one with the right endpoint approximation, I think we can all agree, we're missing out on some of this area. And so because we're missing out on all that area that's there, that means that we have an underestimate. Let me do that. We have an underestimate of the area. 34 units squared is an underestimate of this area. So we need to figure out ways to do better. That's what we really would like. We want to have the best approximation, and that's where integration comes in. So for today, we're just going to be focusing on the area using rectangles, and in a few minutes we'll look at areas using other methods or other shapes, but for now rectangles. Okay, let's go ahead and turn the page. So if I want to find some better approximation using these 4 rectangles, left endpoint was an overestimate, right endpoint was an underestimate, Well, then what about a midpoint approximation? Okay, so midpoint approximation starts off in the same way as it did before. I've got 16 and here's 4, and I'm going to break this into 4 equal pieces. Okay, but this time what I want to do is I want to use the midpoint as the point where I'm going to draw my rectangle. And so in this case, I need to know what is right here f of 1/2. Okay, delta x is still 1. The width between my 4 rectangles is still going to be 1, but instead of using the height at 0 or the height at 1, I'm going to use the height at 1/2. Okay, so let's kind of get this situated. M sub 4. I'm going to have 1, 2, 3, 4 rectangles. The first one is going to be 1 times whatever f of 1/2 is. So we need to figure that out. I'm going to come down here. F of 1/2 means 16 minus 1/2 squared, which is 16 minus 1/4. And so we get, this is 64 fourths, so 63 fourths. So this is going to be 1 times 63 fourths. The next rectangle is going to have the midpoint be on the rectangle, and that's when x is equal to 3/2. So I need to find f of 3/2 to get the height of my rectangle. 1 times f of 3/2. So let's see, f of 3/2 is going to be 16 minus 9/4. So 64 minus 9 is going to be 55 fourths. So this is going to be 1 times 55 fourths. And we're just going to continue in the same fashion, finding the midpoint. This is going to be f of 5/2. If you want to use decimals, you can too. I just like fractions personally. And then the last one, we're going to have the midpoint here at, oops, this was 5/2. This is at 7/2. So 1 times f of 7/2. Okay, so that means I need to find f of 5/2, which is going to be 16 minus 25 fourths. So 64 minus 25 is 39. So this is 1 times 39 fourths. And then f of 7/2 is going to be 16 minus 49 fourths, which will be 15 fourths. Okay, so 1 times 15 fourths. All right, so now I'm going to add them all together. And so I can factor out the 1. It's 1 times these numbers added together. So if I add them together, 63, 55, and so on, this is going to be 172 fourths, which is a nice even number. So I get 43 square units. And I want to decide, is this, well, it's kind of hard to say. Is it an over or an underestimate? I'm not really sure. But in terms of this curve, I think this is the best estimate. In a couple of days, we're actually going to calculate this using integration, and we will see how close we are. Okay, so let me give you an example that is similar in type, but is worded slightly differently. So here I have a table, and it says speedometer readings for a motorcycle given in the table. Find an upper estimate. Okay, upper estimate. And so that means I want whatever is going to be the over estimate for that, for the distance traveled by the motorcycle during this time period using the velocities. Compare this with a midpoint estimate. Okay, so I need to know what's happening with this curve. So my time is going from 0 to 48, and let's see, my velocity is going, I'm just going to sketch this. I'm not going to get crazy here. So 0, 22, 12, 24, 36, 28, 48, 30. So it's going up. And so if I want an overestimate, I have to decide, is that left endpoint, right endpoint, and then it said compare this with the midpoint. So the overestimate in this case is going to be if I draw my rectangle here, and in this case, that means that I will be using right endpoints. Okay, so overestimate in this case is going to be right rectangles. Okay, so I can only use the values that I have in the table. And so I've got 5 values. And because I have 5 values, I'm only going to be using 4 rectangles. If we go back and look for a second at the previous page, I'm not going to be looking at this point at 0, 22. I'm going to start with the velocity at 24. So if I think about this first area here, the delta x value, the width is delta x. And if I look at the delta x values for the time intervals, those are my delta x values. Delta x is the same as delta t, and in this case, that's 12. And then the height, well, that first height is going to be at f of 12. And in this case, f of 12 is going to be 24. Okay, so I'm kind of making a mess of this, but so each of the rectangles are going to have a width of 12. So I'm going to put that out here. And then I'm going to write down the function values at those endpoints, 24, 25, and 28, and 30, right? So those are these 4 values that are coming from the table. This right here is delta x. Each one of those rectangles has a width, or rather delta t, has a width of 12. And then these values right here, these are my velocities. Okay, and so my final answer here, when I calculate this, you could grab a calculator. This is 1,284. And the question is, what kind of units do we have? Well, we're multiplying delta t, which is in seconds, times the velocity, which is in feet per second. And so those seconds units will cancel. This is in feet. Feet. So 1284 feet. That's my upper or right rectangular approximation. It says this time to compare it with a midpoint estimate. Now, the only thing here about the midpoint estimate is that I'm only going to use 2 rectangles. So that's the only part that's a little bit funky, right? Because if I look at the values of, let me go down here for a second. So delta t, I have 0, 12, 24, 36, and 48. So I can go from 0 to 24, and I have a midpoint value at 12, and I can go from 24 to 48 and have a midpoint value at 36. So when I do my midpoint here, I'm actually only going to do 2 rectangles. So my first rectangle, let me zoom in here. My first rectangle is from 0 to 24, has a midpoint at 12. And so that first rectangle has, let's see, 0 to 24 with a midpoint at 12. And the delta t value is 24 because I'm going from 0 to 24. Plus, my second rectangle is going to go from 24 to 48 with a midpoint at 36. And delta t is again 24. So when I compute this, I'm going to have the first rectangle is going to be 24 times whatever that value was at 12. Oh, it was 24. And then the second rectangle has a delta t of 24, and at 36 it was 28. Oops, not 28. AKA 24 times 24 plus 28. This is going to be 1,248 feet. Okay. So a couple of things. These types of problems can be given as a graph, an equation, a table, which is most frequent on the AP exam. And if I'm using equal widths, then delta x is b minus al over n. Typically, we do want to use equal widths. It just makes things a little bit easier. If you give a table, or if you're given a table with unequal widths, here's an important thing to note, is that you must calculate the area of each rectangle separately and add them together. Don't make up data, but you have to do each one separate. And then this last one is just like what we saw in this last example. We had a situation where we had time and we had velocity, and we found that the area underneath that was a distance, right? We had time in seconds, we had velocity in feet per second, and when we multiplied them together, we got feet. And so this is kind of a cool thing too. Area under the curve represents the distance that the object travels. Okay, let's turn the page. Okay, so the big question now that we have these rectangular approximation methods, left, right, and midpoint, we want to get better approximations, and we want to use rectangles for that since we're still on that topic. So in order to get a better approximation using rectangles, what we want to do is we would like to increase the number of rectangles that we use. So if we look at this first figure here on the left, this first figure on the left has 10 rectangles that are being used, but as you can see, there still is a fair amount of error that's living outside this curve. So the middle one, if I go to 30 rectangles, notice that my right rectangular approximation has an approximation that is 0.35 compared to 0.385, but there still is all this extra leftover stuff. And n equals 50, this is going to give us a better approximation. So we're reducing the amount of error that's outside, but like we need to know like how many rectangles are we going to have? Well, what we would like is we would like the number of rectangles to get larger and larger. And so that means we're going to go to infinity, and that's going to lead us to talking about limits. Essentially, what we are saying here is if n is going to infinity, the number of rectangles to infinity, then that means that the delta x value is getting closer and closer to 0. Okay, now the thing is that we don't have to use left and right and midpoint rectangles like all the time, right? So the examples that we saw on the last page was just using the left or just using the right or just using the midpoint. Well, you could actually use whatever the best rectangle is for the region. So if you look at this middle picture, instead of just using one or the other, we can take any rectangle. So let's say I have this blue curve here, and I'm going to use rectangles of equal width so that I have a consistent delta x. But instead of picking left or right or midpoint, I'm going to just pick wherever that rectangle lives on the curve. And so for the first place, whatever that value of x is, I'm going to use the delta x value for my width, but then I'm going to set f of x sub I, whoops, let me undo that. That should say x sub 1 star. And so the star just means like we're somewhere in this rectangle such that I'm touching the curve. The next rectangle, we would have delta x for the width, and then the y value would be f of x sub 2 star. And the star just represents that we're somewhere in the interval on the function. We don't have to be just at the left or just at the right. Okay, so that means that we need to have some different notation. So it says, if we let the width of the rectangles get narrower, we're going to increase the number of rectangles, then the actual area is going to be this. It's a limit. As n goes to infinity of something called a Riemann sum. So Riemann was a German mathematician, And we're going to look on the next page about what does that mean. And N here stands for the number of rectangles. Let's go ahead and turn the page. Okay, here we go with the formal definition. The area, A, of a region S that lies under the graph of the continuous function f is the limit of the sum of the areas of the approximating rectangles. Well, this is not anything new from what we've just learned. We're, instead of setting n to a specific number of rectangles, now we're saying let's let the number of rectangles go to infinity. So we're going to take this as a limit. This right here, as we mentioned on the previous page, this implies an infinite number of rectangles. And then if we look at each of the pieces here, so this first piece is the area of the first rectangle. Area of the first rectangle. We've got delta x, which is the width, and we have f of x sub 1 as the height, wherever that happens to be. And so then here we have the second rectangle, and then we go all the way to the nth rectangle. Okay, so this work was done by, as I mentioned, a German mathematician named Riemann. And so Riemann worked with these limits, and the problem with the limits, though, is that we really are only able to get an approximate area if we're doing it by hand. So as n goes to infinity, we're taking the sum of each of the x values of the function times delta x, and I is going from 1 to n. Okay, this is super cumbersome notation. It really is only an approximation because you still have these little bits. And granted, the little bits that are above and below the x-axis are getting smaller and smaller and smaller. But because we're still using rectangles to estimate this curved region, we're not having exact areas. Well, lucky for us, there is some new notation that we can use, and this notation was developed by Leibniz, also in Germany, and it makes things a little bit easier. So we can we can rewrite this notation with limits using what's called the definite integral. And so here is the notation for our definite integral. And what this does for us is it gives us an exact area, which is great. That's exactly what we want. Instead of estimating the area under the curve, we can find the exact area. Okay, so let's talk about how these are considered equal. Okay, so this notation right here means the same thing in terms of the limit. So let me just explain each of these pieces. All right, so this integral symbol is an elongated S, and it stands for the sum. So instead of using that sigma, the Greek letter sigma, we're using the integral symbol, which is an elongated S. It means sum. At the bottom, we put A, and at the top, we put B. These are called the limits of integration. Limits of integration. And what these mean are where are we starting to accumulate area and where are we stopping. You always put the left-hand value on the bottom and the right-hand value on the top. So then we have f of x, which is, or times dx. F of x is the height of each rectangle, aka it's called the integrand, and dx stands for the width.
aka delta x. But it's not just a fixed delta x, it's right, b minus a as n goes to infinity. So that dx is a different notation that represents delta x, which is the width of each rectangle, but it's not a fixed value because it's b minus a all over n, and n is going to infinity. Okay, so this is our new notation, our integral notation. So one of the things you have to be able to do is you have to be able to translate between these two notations. So let's go ahead and do that on the next page. Okay, so you have to be able to go from one version to the other. And it's easier to go from integral notation, sorry, from summation notation or Riemann sum notation into integral notation. All right, so we're going to try to translate this limit here into integral notation. Let me just rewrite the integral notation here from a to b, f of x, dx. Okay, well, so it tells us right here where we're starting to accumulate area and where we're stopping accumulating area. So this is already telling us A and B. All of this business here, this limit of the sum as the I goes from 1 to infinity, that's just this. So that's nice. Dx and delta x are synonymous, and this function business in the middle goes here. So here's what it looks like. From limit notation into integral notation. It's the integral from -1 to 3. The function, if I just remove the subscripts here, is 3x squared plus 2x plus 5, and then delta x is dx. Ta-da! And that's it. Like, this is why it's so awesome. Because now I don't have to consider each of these individual rectangles. This notation, and when we learn about the fundamental theorem of calculus, will calculate all of the area that's underneath the curve instead of having to approximate it. Okay, let's do one more. All right, this next one, we're going to call this the integral. We're starting to accumulate area at 1. We're stopping at 5. Here is my function, and I'm just going to remove the x sub I star business and replace it with just x. So this is going to be e to the x over 1 plus x, and then delta x is dx. Here you go. Okay, now we would love it if it was always that easy. It's harder to go backwards. So let's do a couple of examples here. We're going to go backwards from integral notation into a Riemann sum. Okay, so I want to write this as a limit as n goes to infinity. The sum I is from 1 to n. I need the function, and in place of all the x's, I need x sub I. If you want to put x sub I star, that's fine. I don't tend to like the stars myself, so I'll just put x sub I because I need to have an I in here because we're going from I equals 1 to n, and then delta x. Okay, so the delta x part is the easiest part to do. Let's talk about what this integral is telling us just before we get further. This is telling me that my function is e to the x, and it's telling me that we are on the interval from 1 to 3, and we're talking about the area under the curve. Okay, well, so let's start with delta x. All right, delta x is the easiest thing to start with. Delta x, because it has a formula, b minus a all over n. B is 3, a is 1 all over n, based on my interval here. And so this is 2 over n. Okay, so, but n is changing. So I'm just gonna be plugging that in here. Okay, so the next thing we need to find out, well, actually, let's do this. So far what we have is the limit as n goes to infinity, summation I equals 1 to n. We still don't know what f, the function is, what is the value of x, but delta x we now know to be 2 over n. So I'm just going to plug that in here. Okay, so now we need to know what goes inside there. So let's take a little side trip here. I'm going to come over to the right part of my paper, and I'm just going to like sketch what this graph is doing. It's e to the x, which is a graph that looks something like this. I'm starting at 1, and I'm going to 3. Okay, so x equals 1 is where I'm going to start. And what we know is that I need to go delta x distance away to get to the next point. We said that delta x in this case was 2 over n. So here would be my next rectangle at 1 plus 2 over n. Okay, then I'm going to do the same thing. I'm going to go over 2 over n to get to the next point. So that means 1 plus, you can say 4 over n, but what I'm working on here is a series. So I really want to look at the series and see what the pattern is. So this is 2 over n times 2. And then if I do it again, I'd be at 1 plus 2 over n times 3. And so that means that each time I'm changing that multiplier, 1, 2, 3, 4, 5, and so on. Okay, well, is there anything in my limit that's going starting at 1 and then going 2, 3, 4, 5, and so on? Yeah, it's here. So my values of x, sorry, it's here, it's I. So if I look at my values of x and what they're doing, I basically have 1 plus 2 over n times I. These are the values of x that are here on my graph that I'm going to be using to calculate these heights. Okay, well, this first one obviously is f of 1. This next one here is going to be f of 1 plus 2 over n times 1. And the next one, height, would be f1 plus 2 over n times 2. Okay, so that means that over here, I have 1 plus 2 over n times I. The 1 is because I'm starting at A was 1, and then this piece over here means that we added 2 over n I times. Okay, last thing we need to do is we need to plug in the function. So the function in this case was e to the x. So finally here, we've got this limit, n goes to infinity, summation, I equals 1 to n, e to the all of that stuff, 1 plus 2I over n times 2 over n. Okay, now you may be wondering, like, why did this seem so much more complicated than before? Well, what we want to do here is we want to plug in all the information that we can. In the previous problem, when we were going from limit notation into integral notation, notice that we were just given delta x. It didn't say anything about what n was doing, and so that's why that was easier. You're not going to see problems where it tells you that delta x is 2 over n or whatever if you're going from limit notation into integral notation. Okay, so let's do another one. From integral notation into limit notation, this should go a little bit faster. Okay, so this means that delta x is going to be b minus a all over n. B is 9, a is 5, and so delta x is 4 over n. All right, so we're going to have the limit as n goes to infinity, sigma I equals 1 to n. Okay, now our function is x squared minus 2x. So it's going to be x squared minus 2x. And then I need delta x, which we just found to be 4 over n. Okay, so instead of drawing the picture this time, in here, where are we starting? We are starting at 5. How much are we adding each time? We're adding delta x, which is 4 over n. And how many times are we doing it? I number of times, right? And I is going from 1 to n, and n is going to infinity. So that essentially means from 1 to infinity. So we're starting at 5. We're going to add 4 over n I times. We have to put that over here as well. 5 plus 4i all over n. And here is your Riemann sum notation for this integral. All right, so you've heard me say that the integral represents the area under the curve. All right, when we say under the curve, what we really mean is between the function and the x-axis. Now, as you know, sometimes functions can be both above and below the x-axis. And when you calculate Riemann sums or definite integrals, you are finding the net area. So that means that areas that are above the x-axis are positive and areas below the x-axis are negative. Okay, now I know that feels weird, right? So areas are always positive. We measure area as a positive quantity. So it's kind of similar to when you talk about positive and negative numbers, right? Negative numbers, like, they don't really exist. They're not countable, but the negative implies where we are on the number line. Same thing as if we talk about negative numbers relative to below sea level. I don't say, when I say I'm like 6 feet below sea level, I mean negative 6 feet, but negative 6 feet isn't something that I can actually measure. I measure the absolute value for its area, or its distance rather. Okay, so the same idea applies here. So let's say, for example, I have this figure 3, and I have 3 regions. So one region is here. Let's call this region number 1. And let's suppose that this region has an area of 2. And then I have this other region below the x-axis. So I'm always going from the x-axis. So below the x-axis here, let's call this region 2. Let's say this has an area of 5. And let's call this region 3. And let's say this also has an area of 2. Well, when I find this integral, or the summation, I talk about the net area. That means I'm going to take 2 minus 5 plus 2, and I'm going to get a negative 1. That means the net area is negative 1. That means there's more area below the x-axis than above it. This would mean that the integral from a to b of this function is negative 1. Now, it is possible to have areas cancel each other out. So let's say that this region 1 has an area of 3. This region number 2 below the x-axis has an area of 6. And this region number 3 has an area of 3. Well, the net area here is 3 minus 6 plus 3, which is 0. So I can say that the integral of this function from a to b is 0. And that doesn't mean that the function doesn't exist. It just means that the net area is 0. Okay, so before we learn about how to do this algebraically, we're going to talk about this integral geometrically by using areas under the curve, between the curve and the x-axis. Okay, so let's start nice and small. it says evaluate the following definite integrals by interpreting in terms of area. Now, later on in the chapter, we're going to learn about how to do this algebraically using the fundamental theorem of calculus. But sometimes you just might get lost and aren't really sure what to do. So you can always do it in terms of area. This is telling us that the function is f of x equals 3, and we're on the interval from 1 to 5. Okay, so I don't know, I don't want to turn this into a limit of Riemann sums. I don't want to approximate it using rectangles. I want to find the area. I want to evaluate this integral, and I'm going to do it using area. So f of x equals 3, that's a horizontal line. And I'm going from 1 to 5. Here is the piece that I'm interested in. Well, that's just a rectangle. And so to find this area, the area of this integral from 1 to 5, 3 dx, is the area, and this is the length times the width. The length is 4 and the width is 3, and so I get 12. Now, I promise you won't have to do all these areas. Once you learn the fundamental theorem of calculus, you'll be happy about that. Okay, let's do one more. F of x is x plus 3. It's a linear function, and we're going to go from -5 to 3. All right, so I'm going to sketch this graph, x plus 3. So the y-intercept is at 3, and it's a line. And we're going to go from -5 to 3. I don't know that my scale is correct there. Anyway, so I want this area below and this area above. So what I have are two triangles. All right. Well, first let's figure out where we are here. When is this equal to 0? That's at -3. All right, so for this piece, area is going to be, let me erase this a little bit so we have some space. 1/2 base times height. 1/2. Okay, so the base is here. That's 2. And the height is here. So I need to figure out where that is. So if I have a slope of 1, I'm going to go to the left 1 to -4 and down 1 to -1. And to the left 1 and down 1 is going to be at -5, -2. You could also just plug in -5 into the function and get 2. Okay, so the area of this region is 2. Okay, now I don't want to say -2. The area is 2. The integral is -2. Okay, on this side, let me make some space here. On this side, area is 1/2 base times height again. And so we have 1/2. My base is 6. And my height, if I plug in 3 into the function, is also 6. And so I get, what is that, 18? All right, so we can do this in a couple of ways. I'm going to integrate from -5 to 3 of this function. Oh, I guess I should write that properly. X plus 3 dx is going to be, if I go from left to right, I can say -2 plus 18, or I can say 18 minus 2. In any case, I get 16. Whoopsie. 16. So we haven't learned about the properties of integrals yet, but you could break this apart. We went from -5 to -3 of this function, and we went then from -3 to 3 for this function, and we found that this was -2 and this was 18, and so we can think about it as two separate integrals. If we're thinking about them as two separate areas, I can also think about them as two separate integrals. Okay, last one. So the last one is requiring that you remember some what your functions look like. This is root 4 minus x squared. Should be something that you are familiar with. If you forget, well, then write it in terms of x and y. You can square both sides and you can move the x squared term to the other side. This is a circle with a center at the origin and a radius of 2. And we're going to go from -2 to 2. So I can sketch this graph. Looks like this. And I'm going from -2 to 2. Well, that's great because this is a circle centered at 0, 0 with a radius of 2. Now, why am I not doing a whole circle? Well, because this right here is positive. There's no negative that's there. So this is the principal square root. It's implying that it's the upper portion. If it was negative, it would have a negative in front of it. And then the area would be negative. In this case, it's not negative. This case here, the area is pi r squared over 2. We know that the radius is 2, and so the area here is 2 pi. That means that the integral from -2 to 2 of root 4 minus x squared dx is equal to 2 pi. So this is one of those cases. We're going to get further on and learn about integrals, learn about the fundamental theorem of calculus and how to do this algebraically. And some people are going to forget, like maybe this is a hard thing to do algebraically, like the reverse of a chain rule that includes a root. So we're going to talk about some strategies a little bit later on in the chapter. Okay, have a great day.